Cloud-native scalability for full-stack developers introduction. Cloud-native scalability is the ability of an application to handle increasing workloads efficiently using cloud-native technologies, distributed architectures, and automated infrastructure. Modern full-stack applications must support: check, millions of users; check, high traffic spikes; global deployments; microservices; mobile applications; web applications; APIs; real-time systems. A common interview topic is: what is cloud-native scalability, and how do modern applications scale? This guide explains scalability fundamentals, horizontal scaling, microservices scaling, front-end scalability, back-end scalability, database scalability, Kubernetes scaling, caching strategies, cloud-native architecture, real-world examples, best practices. This is one of the most important topics for full-stack developers and software architects. Simple definition: cloud-native scalability means designing applications that can automatically handle increasing workloads using cloud infrastructure and distributed systems. Why scalability matters. Applications grow over time. Examples: Netflix serving millions of users, Amazon handling Black Friday traffic, banking systems processing transactions, social media platforms handling viral content. Without scalability, XX slow response times, XX server crashes, XX poor user experience, XX revenue loss. High-level cloud-native architecture. Typical architecture: users, CDN, load balancer, front-end applications, API gateway, microservices, databases, cache, messaging. Core scalability principles. Successful systems focus on: key, horizontal scaling; key, stateless services; key, distributed architecture; key, caching; key, automation; key, observability. Vertical versus horizontal scaling. Vertical scaling: increase server resources. Example: 4 CPU means 16 CPU, 8 GB RAM means 64 GB RAM. Benefits. Limitations. Hardware limits. Horizontal scaling: add more servers. Server 1, Server 2, Server 3, Server 4. Benefits. Cloud-friendly, cloud-tolerant, cloud highly scalable. Most cloud-native systems prefer horizontal scaling. Full-stack scalability architecture: front-end, API gateway, microservices, database layer. Each layer scales independently. Front-end scalability. Front-end scaling involves: check, CDN usage, static asset optimization, lazy loading, edge caching. Technologies: check, React, Angular, Vue, Next.js. CDN, content delivery network. Static content is distributed globally. Examples: images, JavaScript bundles, CSS files. Architecture: user, nearest CDN edge, content delivered. Benefits: faster page loads, reduced backend traffic. Backend scalability. Backend services process, calling, APIs, business logic, authentication, integrations. Common technologies: Spring Boot, Node.js, .NET, Go. Stateless services. Very important cloud-native principle. Bad: user sessions stored in server memory. Good: session stored in Redis JWT authentication. Benefits. Okay, easy scaling, load balancing support. Load balancing. Load balancers distribute traffic. Architecture: users dash load balancer dash server A, server B, server C. Benefits. CURD, high availability. CURD, fault tolerance. CURD, traffic distribution. API gateway. API gateway acts as a central entry point. Responsibilities: check, routing; check, authentication; check, rate limiting; Check monitoring. Examples. Check Spring Cloud Gateway. Check Kong. Check Nginx. Microservices scalability. Microservices allow independent scaling. Example. User service. Order service. Payment service. Notification service. If order service receives heavy traffic. User service means 2 pods. Order service means 20 pods. Payment service means 3 pods. Benefits. Cost optimization. Targeted scaling. Kubernetes scalability. Kubernetes is the foundation of cloud-native systems. Features. Check. Autoscaling. Check. Self-healing. Rolling deployments. Check. Service discovery. Horizontal pod autoscaler. HPA. Example. CPU usage greater than 70%. Create more pods. Benefits. Automatic scaling. Traffic adaptation. Database scalability. Databases often become bottlenecks. Scaling techniques. Shard indexing. Read replicas. Partitioning. Sharding. Read replicas. Architecture. Primary database. Read replica 1. Read replica 2. Benefits. Check. Offload read traffic. Database sharding. Large datasets are split. Example. Users 1 to 1M means shard 1. Users 1M to 2M means shard 2. Benefits. Massive scalability. Caching strategies. Caching is one of the biggest scalability improvements. Popular tools. Redis, Hazelcast, Memcached. Architecture. Application, Redis cache, database. Benefits. COC, lower latency, reduced database load. Message queues. Asynchronous processing improves scalability. Popular tools. Kafka, AWS SQS. Architecture. Order service, Kafka topic, notification service. Benefits. CAPS loose coupling, CAPS higher throughput. Event-driven architecture. Modern scalable systems often use events. Example. Order created, Kafka event, inventory service, email service, analytics service. Benefits. Scalability, resilience. Cloud storage, scalability. Store files outside application servers. Examples. Check. AWS S3, Azure Blob Storage, Google Cloud Storage. Benefits. Infinite storage, reduced server load. Observability. Scalable systems require monitoring. Monitor. CUC, CPU, memory, response times, error rates. Tools. Prometheus, Grafana, ELK Stack, OpenTelemetry, CI/CD, scalability. Modern systems deploy frequently. Pipeline. Code commit, build, test, Docker image, Kubernetes deployment. Tools. C GitHub Actions, C Jenkins, C Argo CD. Security at scale. Important areas. OAuth 2. API Gateway Security. API Gateway Security. Rate limiting. A WAF protection. Multi-region deployment. Large applications deploy globally. Architecture. Canada region, USA region, Europe region, Asia region. Benefits. Lower latency, disaster recovery. Real-world example. E-commerce platform, front-end React application, CloudFront CDN, back-end API gateway, user service, order service, payment service. Infrastructure, Kubernetes, Redis, Kafka, PostgreSQL, scaling flow, traffic spike. Load balancer, HPA, creates new pods. Redis handles cached requests. Read replicas serve queries. Common scalability bottlenecks. 1. Database bottlenecks. Symptoms. Slow queries. Connection exhaustion. 2. Every request hits database. 3. Monolithic applications. Difficult to scale independently. 4. Session-based architecture. Limits horizontal scaling. 5. Synchronous processing. Blocks application resources. Common beginner mistakes. 1. Scaling too early. Over-engineering increases complexity. 2. Ignoring monitoring. Problems remain hidden. 3. No load testing. Scalability assumptions may be wrong. 4. Storing files locally. Limits horizontal scaling. 5. Tight service coupling. Makes scaling difficult. Best practices. Build stateless services. Use caching aggressively. Scale horizontally. Use Kubernetes autoscaling. Monitor everything. Optimize database queries. Use message queues. Separate storage from compute. Implement rate limiting. Common interview questions. 1. What is cloud-native scalability? Cloud-native scalability is the ability of applications to handle increased workload using distributed cloud infrastructure and automated scaling. 2. Why are stateless services important? Stateless services allow easy horizontal scaling and load balancing. 3. What is the difference between vertical and horizontal scaling? Vertical, bigger server. Horizontal, more servers. Limited growth, highly scalable. 4. Redis reduces database load and improves application performance. 5. How does Kubernetes help scalability? Kubernetes provides check, autoscaling, check, self-healing, check, rolling updates, check, service discovery, full-stack cloud-native architecture, users, cloud CDN, load balancer, React frontend, API gateway, SHE gateway, servingcation, user service, order service, payment service, Spring Boot, Spring Boot, Spring Boot, Redis, PostgreSQL, Kafka, read replicas, monitoring Prometheus Plus, Grafana. Final summary. Cloud-native scalability enables applications to handle growing traffic efficiently using distributed systems and cloud technologies. Key concepts include horizontal scaling, stateless services, Kubernetes, caching, microservices, message queues, load balancing, database scaling, observability, automation. Modern full-stack applications commonly use React, Next.js, Spring Boot, Redis, Kafka, PostgreSQL, Docker, Kubernetes. Key idea. Cloud-native scalability is achieved by designing every layer, front-end, back-end, database, caching, and infrastructure to scale independently, automatically, and reliably under increasing load.